Hey pals, good morning, good afternoon, good evening. You're welcome to our lesson today, and we shall be looking at refraction through a glass prism. This is our first lesson in the series, and in case you're new, please just log on to www.teachertaban.com and study with us. This is A-level physics. So to begin with, let's look at the objectives of the lesson. By the end of the lesson, you should be able to at least identify and define the terms: refracting angle of the prism, refracting edge of the prism, and then the principal section of the prism. What are they, and how do they look like? And identify them on the prism. And then you should be able to recall and use the Snell's law of refraction of light, and then use that value to derive the expression for the angle of deviation in the prism. Of course, remember that deviation is the angle between the original direction and the final direction of the light ray. Then, you should be able to identify and calculate for the angles of incidence, refraction, and deviation. That is what we shall be focusing on in this first part of the lesson. So, let's have a look at this. So in this simulation, or in this illustration, we just have different refracting surfaces or refracting materials. Like we have this prism here, we have this other one here, we have the rectangular glass block, for example. We can have a spherical or circular surface, a semicircle, and then this one here. But we shall be looking at basically the prism. So for our prism, we have a source of light, and in case bring our prism there, it looks like that. I can begin with a monochromatic source of light. For example, this one is producing only red light. Remember, a monochromatic light ray is one which is having a single frequency or of the same color. That is a monochromatic ray of light. So we have a ray of light which is red, and then you have our prism. If you look at this prism here, if you look at this ray of light, in case I change the angle of incidence, you can check the way the ray is bent. So at one point, it can even go under total internal reflection, like you can see there, and we shall be able to calculate all of those angles there as we proceed with our lesson. Then we shall also look at, in case we have a white light incident onto the prism, what happens? You can see that the colors are changing. The colors have been dispersed. In other words, they have undergone dispersion, splitting of white light into its component colors. And still you can see how the angle of incidence on one face of the prism changes. So it doesn't change anything. So we shall be seeing this as we proceed with the presentation. So let's go back. So consider the figure below of a glass prism. It looks like this. From this figure here, we can see that this edge here that I'm drawing is what we call the refracting edge of the prism. And these two surfaces here are what we call the refracting surfaces of the prism. We have this angle here. This is the angle of the prism. And finally, we also have this side here, which we call the principal section of the prism. So those are some of the parts of the prism that we need to remember all the way through this lesson here. So how do you define the refracting angle of the prism? You can simply define this as the angle between the two refracting surfaces of the prism. I can take it back a little bit and you see how it looks like. That is the refracting angle. And then we have the refracting edge. We define this as the line along which the two refracting surfaces meet. That is the refracting edge of the prism, where the two refracting surfaces meet. And then the principal section of the prism or the plane is defined as the section perpendicular to the refracting edge of the prism. So in case you go on cutting planes or surfaces along that refracting edge, if they are perpendicular, then we call those ones the refracting, we call them the principal section of the prism. Okay, so let's consider the figure below of the refracting prism. So in case we have our glass prism here, we can begin by identifying these points here. We have the refracting angle of the prism at that point. We have a normal drawn at that point N. If I have another normal drawn at another point M, it looks like that, and all of them meet at a point S. So you can call the line NS as our normal line on one face of the prism, and the normal MS on the other side of the prism. So in case we have an incident ray of light incident at the point N, and that ray ON is making an angle of incidence I1 on that surface there. If the prism was not there, it would simply continue moving in this dotted line here. But because there is change in the refracting media, we have that at point N we have the angle of refraction R1, and then at another point M we have the angle of refraction R2. But at M, that ray of light NM, you can call it the incident ray at point M. But as far as prisms are concerned, shall be calling R1, R2 the angles of refraction. And then, if the light ray was simply going through air, to be going along the dotted line, and because it has been deviated through a small angle, we shall call that one the angle of deviation D1 at that point N. Likewise, if we have the ray NM incident at point M to undergo refraction into air as shown by that ray ME, and the angle between the normal and the ray at point M is called the angle of emergence. We shall call it angle I2. So I1 and I2 are angles of incidence and angle of emergence. But in general, we shall be calling them the angles of incidence, I1, I2. But deep behind your mind, you should be remembering that we have angle of incidence and then the angle of emergence. So, likewise, if there was no prism at that point M there, the ray would simply be coming from behind as shown by that dotted line, and it will be making an angle D2. It will have been deviated through that angle D2. So if this ray of light is extended like this and going in that direction, this would be the angle of deviation D2, and this angle here is vertically opposite to this. So this is how the D2 comes out from like that. So in case we continue, the total deviation D will be the sum of the D1 plus the D2, as we shall be seeing later on. So that is how. So we note that the direction of the emergent ray depends on the angle of the incidence, as we saw earlier on. That in case you change the angle of incidence, at one point the angle of emergence may increase, may reduce, or even the ray may undergo total internal reflection, as we saw at the beginning. We shall be looking at this later on as we move on. So from the figure, you can note that the angle A is the refracting angle of the prism. Angle I1 is equal to I2 is called the angle of incidence at N. R1 is the angle of refraction at N. Then R2 is the angle of refraction at M. I2, which is equal to E, is the angle of emergence at M. D1, D2, those are the angles of deviations at M, at N and M respectively. And then the angle D is the total angle of deviation of the prism. So we need also to recall that of course, I've already mentioned about this, that the angle of deviation is the angle between the original and the final direction of the light ray. So from what you've just seen up there, ON, NM, ME, all those ones are rays of light, as we've been saying that. So from what you've just seen above as well, we can note that if you look at the angle I, remember that we had this diagram like this. We had this diagram like this. We had the incident ray, we had the normal, and this one was supposed to continue like this if there was no change of media. So it was going like this. This was our angle I1, this was our angle R1, and then this is our angle D1, the angle of deviation D1. So from this you can see that this angle is vertically opposite to this, so the two are equal. So I1 being equal to D1 plus R1, it implies that my D1 is actually equal to I1 minus R1. And this is my equation 1. That is my equation 1. So in case you recall, at point M, this was point M, and at this point M we had our normal. So we had our incident ray at this point M, and this was making an angle R2. And if it undergoes refraction, to be going in that direction there. So this is our angle of emergence, which is called I2. So if this one was tending to come from a point behind, then these two angles are vertically opposite. In case I simply elongate this one and this one are vertically opposite, and the two are equal, meaning that this is our angle of deviation at that point M there. So likewise, angle I2 is the same as the sum of D2 plus R2, implying therefore that our D2, angle of deviation at point M, is given by I2 minus R2, like that. So which means therefore that from the triangle NMT, the total angle of deviation D is equal to D1 plus D2, like we saw, and it is coming from this, that if this is our total angle of deviation, this is D1, this is D2, the two interior angles equal the sum of the one exterior angle. So D is equal to D1 plus D2. And if we substitute our expressions, D1 is equal to I1 minus R1, D2 is equal to I2 minus R2. So when you substitute them, we shall be getting that expression there, which implies that our angle D is equal to I1 plus I2 minus R1 plus R2. And remember, I said that the angle of the prism is equal to, or is always equal to R1 plus R2. So we need to always remember this equation here. Always, at least try to remember how it comes about. So for small angle prisms, in other words, if the angle A is very small and it is made of a material with index N, then for small angles in radians, remember sometime back we said that for small angle in radians, the sine I is equal to I. So likewise, for small angle prisms, always the sine of an angle is approximately equal to that angle in radians. So if that is the case, applying Snell's law at N, remember Snell's law at point N, in other words, at this point here we had the angle of incidence I1, and then the angle of refraction R2. This is our point N. So from Snell's law in this format here, our N1 is for air, so it is equal to 1, always remember. So in case we substitute that into our expression, we shall have this. And for small angles in radian, we just say that sine I1 is approximately equal to I1. Sine R1 is approximately equal to R1. So which means therefore that for small angle prisms, I1 is equal to N R1. And still applying the same at M, we shall end up with I2 equals to N R2. And generally, in case we substitute that into our equation for the angle of deviation, we simply substitute for I1 and I2. And since N is a common factor in both of them, if we factorize it out, this is the same as A, which means therefore that in case we substitute for that, we shall simply get our deviation for small angle prisms given by D is equal to A into N minus 1. Please, this is very, very important, as we shall be seeing later on, especially in lenses. So always remember how to derive these two equations. The first one, D is equal to I1 plus I2 minus A. and then for small angle prisms, proving that this is the same as that. So with this, let's try out some few examples before I give you an exercise. So in this question here, the question says that a ray of light is incident in air at an angle of 40 degrees to the normal at one face of an equilateral triangular prism of refractive index 1.5. Calculate the angle through which the ray has been deviated by the time it emerges from the prism. And we've been given those answers there. You can pause the video, try them out, and then we proceed. So let's do it together here and we see. So from the question, I can sketch out this information here that you've been given the angle of the prism as 60 degrees because it is an equilateral triangle. 60 degrees, so the angle there is the same angle here, is the same angle there, 60 degrees. We've been told that the angle of incidence is 40 degrees. And the material is made of refractive index 1.5. So if the ray of light goes like this, at this point, if I call this one my point N, and this one as my point M, the ray of light, we have our normal at point M. The ray of light may be refracted into air, or it may undergo total internal reflection, as we shall be seeing according to the angles that we do have. So if this is our R1, this is our R2. So the question says that we find the angle through which the ray has been deviated by the time it emerges from the prism. So if we are to get the angle of deviation D, we know that the equation is equal to I1 plus I2 minus the A. Or you can simply calculate it from D1 plus D2. The choice is always yours. So let's first get our R1, then we get R2, and then we see if we can also get the angle of emergence. So we shall simply come and say that at N, applying Snell's law, N1 sine I1 is equal to N2 sine I2. Our N1 is refractive index of A is 1 times sine of 40 equals to 1.5, that is for glass, times the sine of R1. So when you check the calculators, we shall get our R1 as equal to 25.4 degrees. So once we get this, remember that A is equal to R1 plus R2. Our A is 60 degrees equals to 25.4 plus R2. This will give our angle of refraction at M, which is equal to 34.6 degrees. So once we get this, then at M, we shall also say that applying Snell's law, we shall have 1.5 sine of 34.6, that is 1 equals to refractive index of air, which is 1 times the sine of angle of incidence in air, which is we shall call it I2. Let me call this one my I2. In case you get an answer, then it means that the ray was going into air. In case you get an answer, in case you get an error, then it means that the ray underwent total internal reflection, as we shall see later on. So when you simplify that and calculate, you'll find that our I2 is equal to 58.4 degrees. 58.4 degrees. So once you've got all of these, then you can come and say that our angle of deviation is equal to I1 plus I2 minus the A, which is equal to 25.4 plus 58.4, then minus the 60. When you simplify this, our angle of deviation is got as 38.4 degrees. Alternatively, some may say that simply we know that our D is equal to D1 plus D2, but I know that my D1 is equal to I1 minus R1, which is equal to 40 minus 25.4. This gives me 14.6 degrees. Then my D2 is equal to I2 minus R2, which is equal to 58.4 minus R2 equal to 34.6. When subtracting those, we shall find our D2 as 23.8 degrees, implying therefore that our D is equal to 14.6 plus 23.8, which gives me 50. No, it gives me 38.4 degrees. So the choice is yours. Let's look at question number 2. Question number 2 says that a ray of light is incident on a prism of refractive index 1.3 and refracting angle of 72 degrees. The ray emerges from the prism at an angle of 43 degrees. Find the angle of incidence and then the angle of deviation of the ray. Still, let's begin by sketching the information for this, and we shall simply come and say that we have our angle of the prism A as 72 degrees. We have the normals. They have told us that the ray was emerging from the prism at an angle of 43 degrees. So calculate the angle of incidence and the angle of deviation. This is our R1, this is our R2. So still, since we've been given the angle of emergence, then it will be better if we begin at the point N. So I'll simply say that at M, applying Snell's law, N1 sine I1 is equal to N2 sine I2. I'll simply say that if the ray is coming from this side like this, this is my medium 1, this is my medium 2 at M. So I have one point, let me see, the refractive index of the glass was given as 1.3. It was given as 1.3. So refractive index is equal to 1.3. So I'll have my 1.3 sine R2 is equal to 1, which is air, times sine of 43. When I simplify this, I'll find my R2 as equal to 31.6 degrees. So once I get the R2 from A is equal to R1 plus R2, this is 72 equals to R1 plus 31.6. So my R1 will be equal to 40.4 degrees. So after having got that, applying Snell's law at N, N1 sine I1 is equal to N2 sine I2. I'll have 1 times sine I is equal to 1.3 times sine of 40.4, implying that my I, when I calculate that, I'll find that my I will be equal to 57.4 degrees. So after having got that, then our angle of deviation D will be got from I1 plus I2 minus the angle of the prism, implying that I1 we got it as 57.4. Our I2 was given as 43 minus the refracting angle of the prism, which is 72. I'll get my angle of deviation as 28.4 degrees. So that is what I get. Alternatively, we can even try it out as D1 plus D2. Get D1, get D2, and see whether we get the same answer as 28.4 degrees. So with this, we're going to try out an exercise in the next section. Please do try it out. Enjoy.